Hello everyone. We'll start with the basic nuclear physics concepts, and this course is targeted for especially the entrance exam, and for preparing the same on a very fast basis. We're going to just discuss about the concepts and also going to discuss some problems in order to solve it, which more or less are coming during your exam. So this is the first lecture that we have on this series, and we are going to break it into first discussing the concepts and some of the formulas which are important. Then we are going to look into the discussion of some previous year questions, and after that we are going to proceed with more advanced nuclear physics properties. So in the basic nuclear physics concept, before we start, we should understand that there are something which is very basic. You might have studied it from your lower classes since you started studying nuclear physics or physics as a matter of fact. Must have studied about the properties of uh, uh, nuclear behavior or the nuclear properties, where you study about its charge, mass, and so on. But we are also going to go into something more deep, like the angular momentum and so on. So when we talk about the nuclear properties, some of the models that we should know are the semi-empirical mass formula, which comes from the liquid drop model. We should also know a bit about the shell model and so on. Okay? These all comes under the theory of the nucleus. As far as your entrance exam is concerned, please keep this in mind that it's not always mandatory that you should know the shortcut of solving a particular problem. If you know the theory well, most of the times you will be able to write down the answers. Yeah, obviously, if you want to top the exam, definitely you need to know a lot of tricks. But even if you don't know too many tricks, but you know your basics right, the chances are that you will get through these exams. So before we start, when we talk about the nuclear physics, it's like certainly different from atomic physics. In atomic physics, we have the basic force, which is electromagnetic in nature. As I keep on saying, please try to remember these things. But when we talk about nuclear physics, we are not talking about electromagnetic force anymore. We are talking about the strongest force present in nature, which is nuclear force, which is a short range force. These things have been explained by a number of observations. For example, we have the liquid drop model, the shell model, and so on. So in your basic syllabus, you have already studied about these things. This course won't deal with the detailed study of this. If you want to go for the details of that, probably you should refer to a particular topic of the same. Now, the study of this theoretical physics involves the study of these various nuclear models. That is more or less the thing. Okay. So when we talk about atomic physics, the order of the energy that we are considering is nothing but 1 electron volt. Okay. So it's 1 electron volt. But when we are talking about nuclear physics, it's nothing but 1 million electron volt. So you can look at the difference here. Okay. So this is basically nothing but for atomic physics, and when we are talking about nuclear physics, we basically can't talk about this in that way. Okay. We will try to understand these properties based on this. So this is also important. So the next idea that we are going to study, charge and mass. So we're talking about charge and mass. If you consider the charge of the nucleus, all of us know that this is nothing but plus Ze. So it's different from that of electron. The sign is positive. And these charges, which are actually determined, are basically determined from the mass spectroscopic experiments and other indirect experiments. Rather, if you remember, we have got something which is called the E/m ratio, and so on. Okay, so using these concepts, the charge has been determined for the nucleus, and Z is very close to an integer. So most of the time, Z is considered to be an integer. But please remember, if you look into the scale and measure it exactly, it might not be an exact integer, but most of the times it is integer. Okay, so you have to remember this charge is considered to be integer most of the times, and Z were different from being an integer. Other observable effects would show up actually. Would show up. So when we're talking about the nuclear masses, they are accurately measured using a mass spectrometer. So when we have the charge interaction, okay, with with an external source. We basically have instruments which are basically called mass spectrometer. It basically measures the charge to mass ratio, okay, by using the electric and the magnetic field. Now, since these electrons are charged particle, the charge to mass ratio can be measured, okay, and we can apply an electric on a magnetic field, based on which there will be a change in the behavior, okay, of the input, which might be an electric or a magnetic field, okay. So the mass spectrometer can be used to determine the relative abundances of stable isotopes, separation of isotopes, and even more accurate method to determine the atomic masses by using the energy balance in nuclear reaction. So next we are going to talk about the density and radius. So when we talk about the density and the radius, the nuclear charge density is empirically given by the equation, okay. So this equation you must have come across before, but let's try to remember this. This is rho r is equal to rho naught, okay, divided by 1 minus e to the power r minus a divided by b, okay. So what are these terms here? This is an important formula, okay, and this will actually give you the charge density, okay, at a distance r. So this a and b are basically nothing but the parameters, okay. A and b are the parameters, and here a can be written in terms of the mass number, okay, and then that is nothing but 1 point, or we can directly write it down to be a to the power 1 divided by 3, and the unit will be definitely Fermi, okay. So the unit is Fermi here. When we talk about B, the value is 1.055 Fermi, okay. So these are some nuclear constants, okay, which are important, okay. We should know. Now what is rho naught? Rho naught is the charge density in the interior. So if you basically consider a nucleus, this is a nucleus, okay. We are not talking about the atom now. Now if you consider the interior of the nucleus, the charge density is nothing but rho naught, okay. So the maximum density that is possible is not, right now we are assuming to be rho naught, okay. And what is rho r? Rho r falls rapidly with decreasing r. So if we are actually going further away from the center, okay, we are actually going to get a different nuclear charge density, which will actually fall off, okay, obviously, and then this will basically be called as rho r, okay. So to remember this, now a is the value of r. So what is a? This a is basically nothing but the value of r at which the density is half the value in its interior, okay. So the density is half the value in its interior. So this will depend on the value of r, okay. So what you can say is a to the power 1 by 3 Fermi is the distance at which the density is half the value of its interior. The parameter b is interpreted in the following way. Basically we consider 2b as the thickness of the nuclear surface, okay. So if we consider something as 2b, we basically say this is nothing but the thickness. So as you know that as soon as we come out of the nucleus, the density obviously will become 0, because there is no more impact of nucleus outside, but within the nucleus the density is definitely there, right. So as we go from outside, from inside to inside of the nucleus to outside the nucleus, we are actually going to see a steep fall in the nuclear density. So if we actually basically just plot a graph between the distance from the center of the nucleus and the density, let's say a function of r, and if we look into the graph, it will be something like this, okay. This is going to be something like this. So obviously if we go at r is equal to 0, right, if we go at r is equal to 0, this density is going to be very high, okay. But as soon as we are coming away or outside the nucleus, this density keeps falling, and it falls quite steeply, okay. So this a is also something which is dependent on this, and if we are basically considering a nuclei, might be this region is considered as nothing but 2b, okay. So this region between these two dashed lines are basically considered as 2b, okay. So this is 2b. So you have to please take care of this, make your notes, because I'm not able to use my stylus properly. I hope I am able to get a good stylus as soon as the lockdown opens. but right now we have to just understand these concepts. Okay, so this is what is happening, and this 2b distance is nothing but the thickness of the nuclei. Okay, so as soon as it comes out, the density obviously falls to 0. Okay, and if we consider something as a heavy nucleus, definitely what happens is the density or the graph would be something like this, because it's a heavy nucleus. Okay, so we can actually feel the impact of the density at a larger distance r. Okay, so that is what is there. So these things, these concepts needs to be remembered. So if you look into the radius of the nuclei, one of the more important relation that you should know, which I guess you are already aware of, is nothing but r is equal to r naught a to the power 1 by 3. Okay, so in order to solve numerical problems and finding out the radii of an unknown nuclei or a nuclei whose mass number is given, you can definitely use these kind of relations, which you are going to see later. Okay, the next topic is angular momentum. Now angular momentum is a term which is different in case of atomic physics and nuclear physics. So nuclei possesses angular momentum, or we basically call it as spin. Okay, so right now if we talk about the angular momentum, let's concentrate on the term spin and not on the angular momentum definition that we know from atomic physics. Okay, now the experimental evidence for these angular momentum comes from the hyperfine structure of the atomic spectral lines using very high resolution spectrometer. Okay, so where do we get this idea from? We basically get the idea from hyperfine structure. Okay, so we have to remember this. So this is hyperfine structure. So if we know the hyperfine structure of a system, or that we studied, we can actually know what is the angular momentum. Okay, so the hyperfine structure will be explained by assuming the existence of a nuclear angular momentum I. Okay, so the nuclear angular momentum is usually denoted by this symbol of I. Okay, and its addition to the electronic total angular momentum J. So if you consider the total electronic angular momentum, that is nothing but referred to as J. So nuclear resonance studies, okay, as well as the studies of beta and gamma transitions of excited nuclei, supports the existence of angular nuclear momentum. And if you consider small I as the total nuclear angular momentum quantum number, let's represent this as small I, which is nothing but the total nuclear angular momentum quantum number. I is it's usually referred as that. Okay, and then basically this is nothing but your spin that we are talking about. Okay, so if you're considering a total nuclear angular momentum of the nucleus, this small I is something which is called the spin. Okay, so this is your spin. So in nuclear physics, the word spin frequently refers to this total angular momentum of the nucleus, but in atomic physics the word spin refers to the intrinsic spin angular momentum only. Okay, so in atomic physics it's the spin angular momentum, in nuclear physics it is the total angular momentum. Okay, so the magnitude I of the total angular momentum, so if you consider the total angular momentum I, it is basically given in terms of h cross. Okay, and then root over I into I plus 1. Okay, so what is I here? I is basically nothing but the nucleus spin. Okay, and if you consider the angular momentum, okay, which is capital I, which is the nuclear angular momentum, which is nothing but actually the part of spin, we can actually write it down the entire term as I is equal to h cross root I into I plus 1. Okay, so to remember this, so the total angular momentum of a nucleus is due to the intrinsic spin angular momentum of the constituent proton and neutron and their orbital angular momenta. Okay, the next topic that we have is called the nuclear magnetic moment. Now the existence of nuclear magnetic moment comes from the studies of hyperfine splitting, okay, of atomic energy level, which results from the interaction of the dipole moments, okay, with the magnetic field due to the atomic electrons. So there can be a splitting of the atomic energy level, which can be actually studied from the hyperfine structure, and this will actually result in the interaction of the dipole moment with the magnetic field due to the atomic electrons. Okay, so if you consider this, we basically have the nuclear magnetic moment. In fact, the nuclear magnetic dipole moment of a proton. Okay, so if you consider the nuclear magnetic dipole moment of I hope all of you remember this, mu n is nothing but E h cross divided by 2m. So this is one more relation that we should actually remember, and if you are considering a proton, the answer should be 0.505, okay, into 10 to the power minus 26 ampere meters. Okay. So let's also try to remember the unit and the values, and this is nothing but the nuclear magnetic moment. Okay, and then we have got something which we call as the quadrupole moment. So nuclei also possesses electric quadrupole moment. Okay, now this is something which is might not be studied in your conventional courses, but that is important again. Now Q, which is nothing but the quadrupole moment, so let me just write it down as here as Q. Okay, so if we write it down as Q here, so the Q measures the extent of departure of an ellipsoidal shape of the nucleus from its spherical shape. So if the Q value keeps on changing, and if we consider the nucleus to be an elliptical shape, and if we know the Q value, and if it's high, the departure from the ellipsoidal shape or the spherical shape, it will become more and more ellipsoid in nature. Okay, it's basically nothing but the Q value. Okay, so the departure of an ellipsoidal shape of a nucleus from its spherical shape. So the evidence of the non-sphericity comes from its hyperfine splitting again. So hyperfine splitting is a very important concept or idea that is being used to study the nucleus in detail. The energy is found to be dependent on the orientation of the ellipsoidal nuclear charge distribution. Okay, so Q in general not zero, but except for I is equal to 0 and I is equal to half. Okay, so Q is not 0. Q basically is not equal to 0. Okay, but Q will be 0 for I, which is nothing but the intrinsic spin of the nucleus, or the angular momentum rather. I is equal to 0 and I is equal to half. Okay, just remember this. Okay, so Q is observed to be 0 experimentally. Okay, but if Q is less than 0, its shape is like an ellipsoid. Okay, so if Q is less than 0, okay, so if Q is less than 0, what happens is we have it like an ellipsoid. Okay, so it will basically become an ellipsoid. Sorry, so okay, we went too ahead. So it is ellipsoid. Okay, on the other hand, who's basically, understand that ellipsoid will have a major axis and a minor axis, right? So this major axis will lie along the z axis. Okay? So this major axis will be along the z axis. So you have to remember this z axis will have the major axis. Okay, so ellipsoid will have a major axis and a minor axis. If you remember this is your minor axis and this is your major axis. Now, on the other hand, if Q is greater than 0, okay, its shape will be definitely an ellipsoid again, but minor axis will be along the z axis. Okay, so the minor axis, it will be again an ellipsoid, and z axis will have the minor axis here. Okay, we are considering a 3D diagram here. So minor axis will be, z axis will be nothing but the minor axis now. So might be this is important for your entrance exam. If they ask you this, what happens to Q less than 0 and Q greater than 0, and that is what is the how the shape of the nuclei will depend on the quadrupole moment. Okay, so nuclear physics talks about radioactivity also. Radioactivity is a nuclear phenomenon, because we are talking about alpha, beta and gamma rays, and in beta we have got the beta plus and the beta minus decay and electron capture and so on, but we are not going to discuss this in detail. Okay, maybe in the future classes we are going to study this. Okay, so right now let's just remember that when we are talking about this, this is will be actually having only alpha, okay, beta or beta rays or gamma radiation. Okay, so this is what is radioactivity is all about, and in beta we actually can have a beta plus and beta minus decay. So this is beta plus, okay, and then this is beta minus. So we've got a beta plus and a beta minus decay. Okay, so now what is the constituent of the nuclei? What are the constituents of the nuclei? So nuclei will have, as we already know, this will have protons and neutrons. Okay, so that is what is the starting point here is. Okay, and the composition of the nuclei has come a long way. Okay, since the time Rutherford's experiment was done. Rutherford's experiment only talked about its charges and all, but not the component. And later on, we found out what are the components, and then beta experiments summed up and suggested that electrons were present in the nucleus. So to remember these historical facts, okay. Now some arguments were also given against the proposition that the nucleus contains electron. So it was also there, but Heisenberg's uncertainty principle came up, and then the belief was widely held that it was given a total entire change into its behavior based on the discovery of neutron in the year 1932 by Chadwick. So then Heisenberg too suggested that the nucleus is composed of proton and neutron, okay, because initially Heisenberg was also not sure of the fact about the composition of the nuclei, okay. So all nuclei are composed of a certain number of neutrons, okay, and a certain number of protons. So basically when we're talking about the total mass number, we basically have the atomic number, we basically represent it as Z, and which is nothing but the number of protons plus the neutrons, okay. So you have got the protons plus neutrons here, and this is totally basically called the mass number. So both proton and neutrons are nothing but fermions, right? So these are what? These are fermions, okay. So this is very basic, but we basically need to know that what are protons and neutrons, and these are nothing but fermions, okay. And if we have fermions here, we are going to use the Fermi-Dirac statistics in any kind of calculations that we are going to do. Right now we are just concentrating on the nuclei. If you go into particle physics, we are also going to come with bosons and all, which we will be going to follow in the later classes. So Z is generally referred to as the atomic number, we should know that, okay. And there are a lot of notations which are used, but mostly the notation is we have the element and we have got the mass number and the atomic number, okay. So just use this notation for a while now, okay. And we will also discuss about elementary particles, and we will try to understand that obviously the neutron is not just neutron, it's a combination of quarks and so on, but we are not just going into that till now, okay. So this was the basics of the nucleus. Now let's go a bit and study a bit about the binding energy, okay. So the binding energy, as all of us know, actually this idea actually came up long back, and we know that the nuclear binding energy is given by E is equal to mc square, delta mc square rather, where delta m is the mass defect, okay. So we should know what is the mass defect, okay, and then after, so this term delta m is the mass defect, okay. So we should remember this is mass defect here, and then mass defect plays a very important role to actually find out the nuclear binding energy. So if we actually consider the mass of the nuclei and the individual mass of the constituents, and we actually compare them, we find that there is a difference which is nothing but the mass defect. And if you take an example for alpha particle, the mass defect is found out to be nothing but 0.0304 U atomic mass unit, okay. So U is basically nothing but your atomic mass unit. So if we individually consider the masses of proton and the masses of neutron and add them up, you get this. But if you use the mass spectrometer and find out the mass of the entire alpha nuclei, you find out that this is the mass. So you can see that there is a difference here, okay. There is a difference between these two, and this difference is nothing but the mass defect, okay. As a matter of fact, you can see that if you consider the mass of the constituent individually, they are more compared to the mass of the entire nuclei taken together. So that means some mass has been lost, which has actually been converted into energy, and that is nothing but we call term as the nuclear binding energy. Now the binding energy of an alpha particle is 28.3 million electron volt. This is itself a very important term. How do we get this? We just simply consider the units, and we will multiply this mass defect by 931.5, okay, approximately. So if we consider and multiply by 931.5, the unit will be in EV, okay, in MEV, and then this is the value that we are going to get. So let's remember this, okay. So if you have the mass defect, you can straight away find out what is the binding energy, okay. On the other hand, I think this is also very handy sometimes to know that one atomic mass unit is nothing but 1.66 into 10 to the power minus 27 kg, and when we convert it into MeV per c square, where you can use the formula E is equal to mc square, and then m you can take it in terms of kg, and then you can keep c on the other hand, and then you can do your calculations by changing it into the units, and then you can get basically nothing but 931.494, which is approximately 931.5 MeV per c square. Please try to remember this. One more thing that is important is nothing but we are talking about this atomic and the nuclear scale, and let's see why they are different in nature. So if we consider a atom, okay, so this the first case is we are talking about only the hydrogen atom, and with the in atom what we have is something which we call as the ionization energy. That means if you actually want to knock out an electron from there, how much energy do we need, okay? Or let's say we want to knock out a proton, okay? When you want to knock out a proton, how much energy do we need in the atom, okay? And that is basically what we call as the ionization energy, and that is nothing but 13.6 eV, leaving aside the sign. So the radius of this positive charge, which is nothing but proton, if you consider the hydrogen atom, is 1.2 into 10 to the power minus 15, so approximately 1 Fermi, right? So that is 1 Fermi. And if you consider the radius of the entire atom, that will be basically nothing but of the order of 10 to the power minus 10, okay? So if you look into this will be nothing but 10 to the power minus 10 in general, okay, approximately, and there might be some, sorry, other values, okay? So we'll just take this as 10 to the power minus 10. On the other hand, if we consider the nucleus as a whole, the radius we know is again 1 Fermi, slightly different on the first point, okay? First part here it's slightly different, but we have again it's the 1 Fermi, the radius of the nucleus. But what we have to consider here is that it's an alpha particle, so that means that within the nucleus itself we have got 2 protons and 2 neutrons, okay? And if we want to put how much energy we should put to break this nucleus, we can actually do the calculation by using the binding energy and so on. We will actually get the answer to be something like this. So what we get here is 283, so we can consider this 28, okay, 28, okay, and then let's say 0.3 into 10 to the power 6, so it's in terms of mega electron volt. So this is basically nothing but 28.3 mega electron volt. And what was the answer for the ionization energy? It's just electron volt, and that's the difference between the energy scales of an atomic and nuclear aspects, okay? So we have to remember this point also, very important. So if you look into the nuclear property, the one of the more important concept is the binding energy curve. So during exam, when you just close your eyes and you should dream about this binding energy curve and able to answer a lot of questions from there, okay? So binding energy curve means it will give you an idea of how much energy is actually needed to break a nuclei for a particular atom, and that can be considered for the entire periodic table. Everything is not listed here because we have a number of atoms here, but in general we can understand this, that iron is basically considered to be most stable of all the atoms, and on the x-axis we have got the mass number. So as we keep on increasing the mass number, the binding energy will keep on changing, because mass number will define what element we are considering, okay, and then we can know what is its binding energy. And then this binding energy per nucleon concept is also very important, okay? So in general, when we write it down, we can also write it down as binding energy divided by A, so per nucleon, okay? So that means if you want to take out a single proton or a single neutron, how much energy do we need, and that is where the binding energy per nucleon concept comes into the picture, okay? So if you consider very light atoms like let's say hydrogen or helium, okay, or lithium, you will basically be talking about this region here. We will be talking about this region. If you are talking about something which is mid-weight, okay, like let's say iron, copper and all, we will be talking about this particular region, okay? And then if you are talking about the heavy nuclei, you are actually talking about this region. So from nuclear physics, you already know that if two light nuclei combine, we are talking more or less about fusion, okay? So this part will actually yield a nuclear fusion in the light nuclei part, okay? And if you are talking about the heavier nuclear part, we are talking about fission, and then this part will actually talk about the nuclear fission part. So the average mass of the fission fragment is about 118. So that means if we have a heavier nuclei, let's say uranium 235 breaking up, okay, we will be basically having two stable nuclei, and these stable nuclei will have a mass which will be near about 118, okay? It's just near, it's not exact, okay? We have got fissionable material whose mass number will actually vary a lot from 118. And the binding energy per nuclei, we have to remember some of the values. For iron, this is maximum, and the value is 8.8 MeV. That's the maximum it can reach, okay? So that means this value is somewhere around 8.8 MeV. As we go to the higher end or to the lower end, the binding energy will drop, okay? and this binding energy curve can explain a lot of features. Okay? So the fission and the fusion can be explained here, because when we talk about fusion, we have two like nuclei which will combine to give a heavier nucleus. So if we have got two hydrogen atoms combining, this will basically give you an alpha particle. This binding energy curve, this peaks that we actually see are because of magic numbers. Okay, so when we look into study the semi-empirical mass formula, okay, and so on, we are also going to study about magic numbers. So for right now, we can say that the magic numbers are the values at which the nuclei will show unusual stability. For example, let's say helium. Okay, so we have something like helium which will actually show unusual stability and so on. So that is why the binding energy becomes more. So what does it mean? That if the binding energy is more, the stability is more. Okay, so the stability is more. So if something is a nuclei will belong to a set of magic numbers, they will be showing unusual stability all of a sudden compared to its nearby atoms. Okay, so that is what is the binding energy curve is all about. We have got a lot of other concepts that we should understand. Okay, and if we consider something like so if we just in general consider something like atomic number 2, or let's say 8, okay, or say 20, okay, or 28 and 52, okay, sorry, 52 and sorry, that won't be 52, that will be 50 obviously, and then we have got something which is 82, okay, and the last one is 126. So atoms which are having these kind of mass numbers will basically show unusual behavior, and that is what we call as the magic numbers. Okay, so binding energy curve per unit or binding energy per unit atom, okay, or the per atom is basically nothing but 8.8 maximum for iron, and it will decrease slowly. Okay, and basically if you consider a mass number of let's say 240, okay, 235 or 240, as a matter of fact, here the binding energy per atom will be decreasing to 7.6. okay, so it will be 7.6. On the other hand, if you consider some light nuclei, the binding energy is well below 4. Okay, and well below 4, even if you consider something as around the range of 6 or 6.5, these are also considered to be having a low binding energy. Okay, so that's very important. Okay, so we should also know the semi-empirical mass formula, and the semi-empirical mass formula will give you a basic idea of the factors on which the binding energy depends, because the binding energy term is not as simple as it looks. They basically call as the Whittaker semi-empirical mass formula, and there are some parameters which are observed, which is nothing but the constants you can see, A, V, A, S, and so on. And these are actually obtained empirically by fitting measured masses. Okay, so if you look into this semi-empirical mass formula, the terms that we have is AV. V is the volume term. So this is the only positive part in the semi-empirical mass formula which adds to the binding energy. So if the volume is more, the binding energy will be more. But there is a term which is the surface term which reduces the binding energy. The Coulomb term will reduce the binding energy. The asymmetry term will reduce the binding energy, and finally the pairing energy. Okay, so we are not going to go into the detail, but from an examination point of view, we should remember the formula. And if we consider the pairing energy here, in the pairing energy part, it will basically be 0 if we are considering a odd even nuclei. Okay, so we have basically got this as 0 if we are considering an odd even nuclei. So what does it mean? That we have got an even number z or an odd number n, or the other way, even number n or odd number z. Okay, but on the other hand, if z and n are both even, then this pairing energy is plus delta naught, and if it is odd, this pairing energy would be nothing but minus delta naught. Okay, so this sign will actually change depending on whether it's z and n are even, then it will become positive. If z and n are odd, this will become negative. On the other hand, if z is odd and n is even, or n is odd and z is even, we are going to have a value of 0 for the pairing energy. Okay, so if we look into the values here, should now remember these values which are important. sometimes they don't supply the value, so we should know it. So the volume term, this would be nothing but 14 million electron volt. The units will be million electron volt. Let me not write down the values in, okay, let me just write down the values here and not the million unit here. And then the coulomb term, or sorry, the surface term is nothing but 13 electron volt. Okay, and then we have got the coulomb term, which is nothing but 0.60. Okay, and then we have got the asymmetry term. The value is nothing but 19 million electron volt. So you can see, if all the terms are actually present, in fact you are going to get a binding energy, okay, which will actually vary. Okay, and the binding energy actually depends on this mass number and also on the atomic number and so on. So every factor has to be considered, and then finally you can get what is the binding energy using the semi-empirical mass formula. You should remember these values. On the other hand, if we consider something as the pairing energy, okay, which is this will be basically nothing but 33.5 MeV. Okay, 33.5 MeV, which is positive. If we have a even, or let's say odd nuclei. Okay, so if we have got odd numbers of nuclei, okay, for this case, for the odd case, okay, this is going to be plus. Okay, this is going to be plus. But if we have Zn and even, we are going to have minus 33.5. Okay, this is minus 33.5 for Zn even. So please remember, this sign, this particular sign will actually depend on whether it's a Zn are even or Zn are odd, and the value of delta naught will depend on the signs will be different here. Okay, so if it is Zn are, it's an odd nuclei. Okay, it's an odd nuclear system, this will actually have a negative sign there. Okay, this is for odd, and then this is for even. Okay, and finally you can check the answer. So that's your semi-empirical mass formula. Okay, so we have seen some basic properties of the nuclei. We have talked about binding energy and semi-empirical mass formula in general. We have not gone into the detailed theory of this. In the next class we are going to look into the some numerical problems which can be solved using these ideas. Okay, thank you.